Hi, today let's have a look on this device. So this is a cabin temperature controller, according to the seller. This thing was manufactured by Normalair Garrett Ltd. The reference of this thing is 481 TC. I didn't find anything on internet about this device. This is a light box. Let's open this thing to see what is inside. Okay, so we have different small boards, an output stage, a transformer. You can see there are two transformers, the power supply, a modulator, limit and startup, and a bridge integrator. So this is the most interesting board. You can see the integrator capacitor here. Okay, so let's start with the first one, the bridge integrator. On that board there are two ICs. This one is a dual op-amp 747. The second one I cannot read. The second one is a UA108, is an op-amp, dead code 83. This should be the bridge for the sensor, obviously. And the sensor is one leg of the bridge. You can see that this signal is inside a guarding track connected to the ground, obviously. One connection of this signal is one side of the capacitor, and the second is this resistor, which is the input resistor probably. So the value should be large normally. I try to read. Okay, so this is a 820 kilo ohms resistor. Okay, and the other pin of the capacitor should be connected to the output of the op-amp. It seems to be this track here, this one, and we can see effectively it goes to that side of the op-amp, so this is probably the output. And this leg of the resistor should be connected to the output of one of these two op-amps, which is the error amplifier. Okay, we can see that it is connected to that resistor here, which is connected effectively to one pin here. So this is the error amplifier, and the output is connected to the integrator, which is this op-amp. So this op-amp is probably a specific op-amp with a very small bias current. As you can see, this capacitor has a shield. The shield of the capacitor here is connected to this terminal. And there is a design error, because normally the shield should not be connected to the input of the op-amp, because this node is very sensitive. This is a virtual ground. If you connect the shield of the capacitor to the output of the error amplifier, in that case it is not sensitive. Normally this capacitor should be reversed. The second board is limit and startup. On that board there are a few resistors and two op-amps. These two op-amps are 747 dual op-amp. This is the modulator board. I don't know exactly the purpose of this board, but we have two nice capacitors, 4.7 microfarads. We have one dual op-amp. You can see this board is symmetrical, and there are two NPN transistors, two N1711. This is the power supply board. There is also a relay. There are two transistors, two N4912 and 4900. This is the transformer board. There is a diode bridge here. So one transformer is connected to this bridge rectifier, and the second one is connected to the connector. I don't know the purpose of this transformer. Last board is the output stage. There is almost nothing on this board except two relays and RC network. These are snubbers. You can see the relay from Teledyne, dead code 84. The reference is 682-1. These relays permit probably to drive valves for warm and cold air, probably, in order to stabilize the cabin temperature. The rest are card edge connectors and also a flat flex. I have done the complete reverse engineering of this cabin temperature controller. You can see the complete schematics on this page. Let's start with the left circuit here. This circuit corresponds to the bridge and integrator board, this one. As we can see on the left, we have a bridge, and you can see that one leg is missing, and these two signals are available on the rear connector, so obviously there is a temperature sensor which is connected between these 2 points, so this permits to have a complete bridge. We can see also that this resistor has a common point with this one, and the second leg is available on the rear connector. So I assume that there is a potentiometer which should be connected between the pins M and H here in order to have the preset temperature. So this permits to change the value of this resistor here. In the middle, we have a differential amplifier. The inverting input is connected to that point, and we can see that the positive input here is available on the rear connector. So I assume that there should be a short circuit between pins L and M in order to connect the positive input to the other output of the bridge here. The signal at the output of the differential amplifier is fed to this amplifier with a gain of minus 13. At the output, we have a resistive divider, 6.2K and 220 ohms. And then we have the integrator. The reduction of the voltage as the input of the integrator permits to artificially increase the value of this resistor. There are two outputs of this board. One I called P, this is proportional, so this is the voltage which is proportional to the difference between the actual temperature and the preset temperature. And the second one, I called I, corresponds to the integral of the error. So this is obviously a proportional integral regulation. These two signals are fed to the second board, which is the limit and startup. We can see on the left that these two signals, proportional and integral, are converted into a current. This is the summing node, which is a virtual ground. So the output of the amplifier is proportional to the sum with some coefficient of the proportional and the integral error. And we can see that the voltage at the output is limited on positive and negative using this diodes arrangement and these resistors. Following this limiter, we found an amplifier here, and the second one with a gain of -1. The outputs of this board are two signals, one positive and one negative. These two signals are fed to the modulator board. The modulator board permits to convert these two error signals to two rectangular signals, which are available on terminals 4 and 3 here. Actually, one signal will be used to activate the heater, and the second one will be used to activate the cooler. The modulator permits to convert the error input voltage, which is positive here, into a signal which duty cycle depends on the actual voltage here. Each output drives on the output stage board a solid state relay. One is here and the second one is here. There are these two relays here. These relays permit to drive motor or a servo valve or something like that in order to adjust the cooling and the heating of the air. We can see on the bottom of this page here a small circuit which permits the detection of the overcurrent. The sum of these two currents flows into that fuse and this sensing resistor here, which is a big 10 ohms resistor. We can see here on that board. The voltage across this resistor is fed to the transformer here. It is this one here. On the secondary side of this transformer, we have an AC voltage which is proportional to the current flowing through that line here. The voltage on the secondary side is rectified using these 4 diodes. This voltage is fed to the power supply board. The power supply board schematic is not complete. There is just the circuit which permits the detection of the overcurrent. The voltage at the output of the rectifier is filtered using this capacitor. There is also a diode which permits to limit this voltage. So when the voltage is above a given limit, this SCR turns on, and this permits to activate the relay. This is this small relay here. When there is no overcurrent, the relay is on that position here. We can see that we have two signals which are available on the rear connector. The signals are connected to the bases of these two transistors. These transistors permit to shut down the output stage, so it is possible to deactivate the heater or the cooler using an external signal here. So I don't know exactly the purpose of this thing. When there is an overcurrent, these two inputs are disconnected. This was the teardown and the reverse engineering of this cabin temperature controller. Thanks for watching and see you next time. Bye bye.